wait a moment to ring the bell? Or...
The bell has been rung.
Okay, so we can start.
We can start.
Okay. Well, good morning. It's my pleasure to introduce the first talk by Agustina Czenki from University of Southern California about unoriented two-dimensional TQFTs in the category WebST.
Thank you for the introduction and thank you all for being here. I decided today to tell you about one of the problems that I worked on during my PhD. And this was on two-dimensional TQFTs. What I'm going to tell you today is a bit of the story in the oriented case, which was something that was already known when I started my project. And then I will tell you work that was known in the unoriented TQFTs and what I worked with in here. So all of my work was in the unoriented setting. Yes.
Maybe you should shift the little video because it covers this up.
Maybe here?
Yes.
So in the oriented case, I'm here talking about two-dimensional TQFTs. We know that an oriented TQFT, so the data for having a symmetric functor like this is the same as the data of a commutative Frobenius algebra in the target category. And I will be telling you all of the details about this. And from here, from this category of two-dimensional cobordisms, people have been able to reconstruct the category RepST, which interpolates the category that we all know of representations of the symmetric group from n, a natural number, to t, any number in field. Then people were looking at what happened in the unoriented case, what happened when we lose orientations in all of the cobordisms. And it turns out that having the data of a functor like this is the same as finding an extended Frobenius algebra. So I will tell you what this is. And my work here was to try to mimic what was done for the oriented case and see what happened in the unoriented case and what algebraic constructions, so what algebraic categories we could recover from coming from topology, coming from two-dimensional cobordisms. So that's what I'm going to tell you about. I'll be going through some of these slides a bit fast. I know that people in the audience have different backgrounds, so feel free to stop me. So I'm going to be working on algebraically closed field of characteristic 0. And we're going to be talking about k-linear categories. So home spaces are vector spaces, composition is bilinear. Additive means k-linear, and for any two objects, we have the direct sum in the category as well. And Carubian, which will come up, means that the category is idempotent complete. So you can always split an object whenever you find an idempotent. And one thing that we will be using, or that I used in the construction, is that whenever you start with a k-linear category, you can consider its additive completion. So you formally add all of the direct sums, and then you consider its Carubian envelope. So again, you're formally adding all of the idempotents. And when I say monoidal, I mean I have a tensor product. And the one thing that I wanted to say is whenever we say tensor in this talk, we mean k-linear and monoidal. Sometimes tensor also includes abelian, but not in this talk. We're going to be working with things that are at most Carubian, not necessarily abelian. So, well, this we've been talking about a lot during these 2 weeks, but abrading, that's an isomorphism that commutes two objects in the category. We say it's symmetric. If when we do it twice, we get the identity back. And the category of cobordisms and dimensional cobordisms is a symmetric monoidal category. And so will be the category of unoriented and dimensional cobordisms. Here in the slide, I know we've been talking about cobordisms a lot, but I still want to at least say it quickly, just in case. So when I talk about cobordisms, what I mean is the category that has objects n-1 dimensional closed oriented. So everything here is closed, everything is oriented. Maps are, well, classes of cobordism. So a cobordism is an n-dimensional oriented compact manifold. And we're saying a cobordism goes from an object X to an object Y if we have some way of identifying the boundary of the manifold with the disjoint union of X and Y. And we identify one of them as the in boundary, one of them as the out boundary, and everything here preserves orientation. So when we talk about oriented cobordisms, orientation is playing a role in every part of this definition. And gluing, of course, is you glue, the composition is gluing, which is you put the boundaries together. So here, I'm showing how if we have two cylinders, we can glue them, we can compose them, and then we come up with a torus. And we will see how we have different compositions of cylinders when we're talking about the unoriented case. Okay. So in this talk, everything will be two-dimensional. So the picture that you should have in your mind is something like that, like what you see there. Any connected cobordism is it's going to look like this. And we can think, or we will think of objects as natural numbers. Why? Because we're thinking about closed one-dimensional surfaces oriented, so we can just, as an isomorphism class, we can just always go back to the circle, and so objects will just be stacks of circles in this sense. And so how many circles we have is the number that we identify the objects with. And then, well, if we are having something connected from M to N, it will look like that picture right there. And like I said, this category is going to have a symmetric monoidal structure. So what is the tensor product? If you're doing the tensor product of objects, that's just the sum. And if you're doing the tensor product of two cobordisms, you just put them together, one next to the other. So you can see how we start from something from 2 to 3, and something from 1 to 2. We end up with something from 3 to 5. The braid, so again, we want to say what the braid, the symmetric structure is. So the braid is this cobordism right here that switches the circles. And when we do it twice, they are in this one that goes like this twice, and the one that's just two cylinders, they are in the same class. So they are the same in the category of two-dimensional cobordisms. So the reason why we were thinking of working with two-dimensional things is because the category of two-dimensional cobordisms oriented. This first part of the talk is all about oriented. It has a very nice algebraic description. Like you can kind of forget about the topology, which is the original definition. Everything is defined by using just topology. And you can instead think about a category that is given by generators and relations. So the way that we can think of this two-dimensional cobordism category algebraically is by having these 5 generators, which means every other map in the category will be made of either composition or stacking, horizontal stacking, or using the braiding, but I just need those that are right there. Every other cobordism I can just draw by using these 5 drawings. And I am showing just a little, a couple of examples of how I can come up with a sphere, the torus, the punctured torus with just these 5 generators right here. And so we can, when we talk about dimensional cobordisms, we can just say, we are looking at the category that has these 5 generators and they are subject to these relations right here. So in that way, we forget about the topology in some sense, and we just think about it like this. You can see here these, you've probably seen this before, some of you, and if you haven't, these probably look familiar because they look a lot like the drawings that you would have for an algebra. The first line, right? The second line for a coalgebra, and then the third line is what we call the Frobenius relation. And so here you can already picture why having a two-dimensional oriented TQFT will be the same as finding a commutative Frobenius algebra. Because the category is simply defined by these 5 generators satisfying these relations right here. Any questions so far? So basically, the picture to have in your head is that any connected map looks like that. So we have some in part, some genus in the middle, and some out part. And now that we know what things in this category look like and how we can think of it algebraically, the next step, so this is what I'm going to be talking about, is work by many people, but the next step is coming up with a linearization of COP2. So far, things are not linear, right? We just have a monoidal structure. We want to make it k-linear, so that's what we're going to do first. And then our second step will be to make home spaces finite dimensional. We want something that is more controlled. So let me show you first why we are interested in Frobenius algebras. So let's see any symmetric monoidal category. Then an n-dimensional TQFT is a symmetric monoidal functor from the category of oriented cobordisms to C. And I want to emphasize here that I'm using C, any symmetric monoidal category. Sometimes people just like to use vector spaces, but we could replace vector spaces by any category C. And this is sometimes called a C value TQFT. And I said, well, this data is the same as just picking a commutative Frobenius algebra in C. Like the only thing I need to be able to define a two-dimensional TQFT is this algebra. So what is a Frobenius algebra? A Frobenius algebra is an object A in the category C that has 4 structure maps: a multiplication, a unit, a commultiplication, and a co-unit. And you can see, well, first I want A with multiplication and unit to be an algebra. So, and then I want it to be a coalgebra with the commultiplication and the co-unit. And then I want to ask for some relation in between the multiplication and the co-multiplication maps. And that is the diagram that you see right here. So some examples, let me give you some examples of Frobenius algebras, because then I'll be telling you about extended Frobenius algebras, and it will come from this. But you can always think of the trivial algebra, right? Just the field where you're taking your co-unit to be the identity map. Or maybe you could think about group algebras, KG, so for any finite group G, where your co-unit just takes the unit to 1 and every other invertible object to 0. So these are examples of Frobenius algebras in the category of vector spaces, but you can find Frobenius algebras in any symmetric monoidal category, and we will see a bit more about that.
Do you assume finite? Like, do you have to be finite here? Does your Frobenius algebra need to be finite?
You mean
dimensional?
Finite dimensional? I think it's a result of being a Frobenius algebra that you'll be finite dimensional. So they are finite dimensional, yes. Good question. So let's say we have then a symmetric monoidal category C, and we have a commutative Frobenius algebra in C. So why are we saying that this is enough to define a two-dimensional TQFT? Well, remember that we're thinking now of our category of cobordisms given by generators and relations, and that's what makes it in a way nice to be able to define a functor, because if we have the category by generators and relations, then all we need to do is say where the 4, I'm using the cylinder which just maps to the identity, right? But where do the other 4 generators map? And as long as we map them to something that satisfy the relations into the category of two-dimensional cobordisms, then we are done. This is a well-defined functor and we don't need to do anything else. That's why it is really nice to have it, a description like that by generators and relations. So we say, well, if we have a Frobenius algebra, if we find the Frobenius algebra in C, we can just map the cylinder to the object A, and we map the generators to the corresponding structure maps coming from the Frobenius algebra. And because this is a Frobenius algebra, it will satisfy the relations. It will be a well-defined symmetric functor. And I just wrote here just so that you can see, for example, we have that condition in the definition of a Frobenius algebra, which says how the multiplication and the co-multiplication interact with each other. And this translates exactly into the relation coming from two-dimensional cobordisms. And the same for all of the other relations. Remember that we said, well, this one means it would be an algebra, this one a coalgebra, and this is the Frobenius relation. And the other way also works, right? If we have a TQFT and we look at the image of all of these, the circle and the generators, then what we get in the target category is going to be a commutative Frobenius algebra. So that's how this works. Okay, so now we know this, let me tell you how we start to linearize this category, the category of two-dimensional cobordism. So this is work by many people. So a lot of people have been working on this and doing different types of constructions with this. I want to mention Kovanov, Stanovic, Ostrich, Kononov, there are many papers. So we start with a sequence alpha of numbers, just any numbers, right, in the field. And what we want to do, of course, is allow linear combinations of cobordism. So that's our first goal. Our second goal is to, in a way, get rid of closed surfaces. So every time we have a closed surface, we are going to replace it by a number coming from the sequence alpha. So what do we end up with? We will end up with a category. We call it B of alpha. Alpha is because it depends on the sequence you start with, right? Because that's how we're evaluating your closed surfaces. And the B, I believe, comes from viewable cobordisms. That's what they call it. When you eliminate surfaces, you call this viewable. And so now objects are still the same, right? They're stacks of circles. So we're still thinking of the objects as natural numbers. But now maps, first of all, we have linear combinations, right? We are allowing formal sums of cobordisms with coefficients in the field. And also we don't have any closed components. Any closed component gets automatically replaced by a number. And the composition now is gluing, and then of course you have to evaluate. What does that mean? If let's say we're composing something like this, then we get a picture like that, but this right here is a closed surface, so we have to replace it by the corresponding number. Okay, so this is our first step. Now we have something that is k-linear, right? We can do formal sums in home spaces, but the next thing that we want to do is make things be finite dimensional. So of course, if you think of just the home space from one to one, right? From one circle to one circle, any a cobordism from a circle to a circle can have any genus. Those are all going to be linearly independent cobordisms. So we want to restrict this category in some way so that we can have something that is finite dimensional instead. So this is the second construction. This is called the Skane cobordism sub alpha. And let me tell you first, so what is our goal? Our goal is to have finite dimensional home spaces, right? And like we said, the problem is that if you look at the home space between two numbers, you can have any genus. So what we want to do is control the number of holes you can have on a cobordism. And that's why this is the main thing that we're going to be looking at, this cobordism right here. We want to restrict the category in such a way that you cannot just have any holes for a given cobordism. So let's look at this. We call it the handle cobordism. It's the one that just has one genus one. And so what we're going to do is quotient the category, but by something that restricts the number of holes that we can have. So how do we do this? I'm not going to be giving all of the details, but I'll explain how the construction goes. We first define a trace in the category of viewable cobordism. So how does this trace work? Whenever we have a cobordism from n to n, like you can see here, something from 3 to 3, we just close the respective circles with a ring. And so once you close this, you get something that is well, a closed surface. And we can evaluate it the way that we've been doing using the sequence alpha that we started with. Because we end up with something that has genus 5, I replace the trace of that cobordism will be alpha 5. So that's how I get a number back. And so when I look at this, this handle cobordism, the one that has genus 1, and then I can compute the trace for any composition of this. So if I have n as the genus, then when I close it with a ring, I get alpha n plus 1 because that goes up in the genus by 1. And so what I'm going to do to control this is I'm going to start with alpha, not just any sequence, but a rational sequence. A rational sequence just means the generating function of alpha is a quotient of 2 polynomials. And why do we want to start with a sequence like that? Because having something that's rational is equivalent to your sequence satisfying a linear recurrence. So there is some number, bold k, that you see right there, such that for any number bigger than that, when we have alpha k, we can just write it as a linear combination of alpha i's that are smaller than k. So what this means for us in our construction is that whenever we have something that has genus big enough, we can just, our goal is to replace it by a linear combination of cobordisms that have genus lower than that. That's going to be the goal, and that's why we're going to use a linear recurrence like this. So how do we do it? Well, this is where the technical part comes in. We want to be able to quotient our category by tensor ideal of negligible morphisms, or we can close it by a tensor ideal inside a negligible morphisms. Negligible morphisms are morphisms that have trace 0 in the category. And so if I look at this cobordism right here, so the cobordism that has genus k, when I compute the trace of this, so something that has genus k and a linear combination of things that have genus less than k, I get exactly this linear recurrence, which means I get something that has trace 0, and I can just quotient my category by that. And yes, I'm not giving the technical details, but what this will mean in this quotient is, again, every time I have something that has genus bold k or higher, then I can replace it by a linear combination of things that have genus less than that. And that gives me then that I have finite dimensional Hom spaces for any 2 numbers. Any questions?
Good.
Yeah.
I think I missed maybe the motivation. Why do you need a linear structure on the category of cobordisms? Like to define the TQFT, like let's say.
Oh yeah, so what we're gonna do is not that we need it, but we want to be able to reconstruct algebraic things, so algebraic representation categories from cobordisms. And because of that, when we take the category of cobordisms and then we linearize it, then we make it finite dimensional and we see what we get when we do those steps. And now we will see how the TQFT, like what do we mean by a TQFT now, when after we've linearized it and done this. So yeah, before we had a 2-dimensional cobordism, so that was a symmetric tensor factor from COP2 to C. So what would it mean to have now something from the viewable cobordism category? Remember, this one is the one that still has infinite dimensional Hom spaces. So the only thing that we did was linearize it, like make it k-linear and also replace closed surfaces by numbers. Well, then the data that we will need to be able to define a functor like this is to find, of course, a commutative Frobenius algebra in C. And what we need to make sure is that that commutative Frobenius algebra that we find also has evaluation alpha. And by evaluation, we mean that when we do these compositions, so remember the Frobenius algebra comes with a multiplication and a co-multiplication. So when we do the same type of diagram, so this would basically be this picture. We're doing unit, co-multiplication, multiplication, and co-unit for this one right here. And this is the closed surface of genus 1. So we want that to again be alpha 1 also in C. So, and then we do the same thing, but in this one we do co-multiplication, multiplication twice, which means we have genus 2. We want that to be alpha 2 and so on in the category as well. And that will give us a well-defined functor in between these two categories. And now when we take alpha rational and we can make this other construction that has finite dimensional Helm spaces, then to still have a functor, what we also need is for F to annihilate the handle relation. Remember that the difference between this category and the previous one is that this comes from the quotient of the other one by this handle relation that makes it so I restrict the genus number underneath cobordism. So now that we know how to construct this, basically the point of this is if I want to see what I get when I do a construction like this, so I want to see that this is equivalent to some other category C, then I know in principle, I would know how to start building such a thing as long as I can have a category that has a Frobenius algebra with that evaluation. And that satisfies the handle relation. Like if I can have those two things, then I can find a functor and then I can wonder whether it's an equivalence. So that's what this is about. This is how do I know if I have a functor to begin with, and now if I want to see that these two things are the same, then I can wonder about that. But first I need to find the commutative Frobenius algebra, and I need to make sure that I have this handle relation being satisfied. And like the title of my talk says, I'm going to be talking about the category C. So what we're going to see now is that this construction, this thing that we just did, linearizing and then having this quotient will turn out to be the category rep ST, which is algebraic, right? So that is kind of the relation that we're trying to see here. We start with the category that's purely topological, two-dimensional oriented cobordisms. We get a representation category. They're equivalent. So I just wanted to first at least have a couple of slides explaining what the category rep ST is. I'm sure everybody's familiar with the category of representations of a natural number, rep Sn. This category, we say, interpolates it, so it generalizes it in a way. This category is very interesting and people study it a lot. Why? Because it's an example of a category that has exponential growth, right? A lot of the examples that we come up with, like when we're talking about representations of groups and things like that, those have moderate growth. The category rep ST has exponential growth. It's very, very big. It grows up rapidly. Also, let me tell you, when T can be any number in the field, right? When T is not a natural number, rep ST is semi-simple. But when T is a natural number, this is not semi-simple. It's not even abelian. And the way that we say that it generalizes it is because there is a functor when we have a natural number from rep ST to rep Sn. We have the functor. It's not faithful because it sends some non-zero things to 0. But when we go through a process of semi-simplification, then we will get the category rep Sn that we all know. Okay, so I'm going to show you here, not the original definition of rep ST. I am using another, like a diagrammatic description. This is by Holmes and Ostrich, which uses partitions to define it. So I'll show you first the partition category and then how you reconstruct rep ST. And the reason I'm doing it is because the drawings will look more like the drawings we've been seeing before, and it will make maybe a bit of diagrammatic sense of why these two things are connected. So let's talk about the partition category first. Here, objects are just numbers. You can think of them as numbers. In the diagrammatics, it's going to be dots, right? 1 dot, 2 dots, 3 dots, depending on the number. And so the home space from N to M is going to be generated by all partitions of N plus M. So you can see here, I did a couple of examples of what a morphism from 2 to 3 is. I'm reading here from top to bottom. So I write 2 dots and 3 2 and 3, 2 and 3. These are all from 2 to 3, and then I just do some partition, and these maps are all different. And of course, there are more, right? You could do many other partitions in these 5 dots that we have right here. But each one of those is a map in here, and then I can do linear combinations of this. And then composition, so I think it's easier to explain with an example. Let's say I have a map like this and a map like this. So how do I compose these 2 partitions? I stack them, sharing the middle part, as you can see here. Then the middle part gets eliminated, and I just draw it like that. These were connected because of this, so they're in the same bag. And for any closed component that is in the middle, that shares nothing with the top or the bottom, I multiply by a factor of t. And that's where t is finally showing up, right? In the home spaces. We so far haven't talked about category, and we say this is the partition category P sub t. This is where t shows up in composition. So we start with this partition category, and the unit is going to be 0. The tensor product, same as with cobordisms, is concatenation. You can see here the braiding. And so how then do we define the category rep as t that we were talking about? Well, we start with the partition category. We do its additive completion, which we talked about at the beginning, which is just I make I have all of these direct sums now of objects, and then I take its Carubian envelope, which we also talked about in the beginning, which is I make it idempotent complete. So I start with these diagrammatics, and then if I formally add all idempotents and all direct sums, I will get the category rep as t. So how is it that rep as t is connected to the category cohort? It's right here. So we are going to start, remember that we can start with any sequence that is rational, that satisfies this linear recurrence. So what happens if we in particular look at a sequence that's constant? Here alpha 0 is some like not 0. And then the generating function for that, the constant sequence looks like this, alpha 0 over 1 minus t. What that means for us is that the handle relation, remember this relation that comes from the recurrence, looks like x equals the identity. Why? Because alpha 1 equals alpha 0, right? That's the whole relation we have. So genus 1 is genus 0, genus 2 is genus 0. If you want to think about it like that, that's what's happening. Every time we have genus n, that's the same as genus 0. So every time we have a handle morphism, it gets replaced by just a cylinder. So basically, everything is genus 0 in this category. And now, so let's think about then how a map from 0 to n will look like, right? From 0 to 1, things have genus 0, so that is our only option. From 0 to 2, we can only have these 2 things. From 0 to 3, we have this, and then this is just so maybe you can see why this is related to partitions, right? If things all have genus 0, then we just need to choose how things are connected to each other, and that's it. And that is kind of the same pictures that we were having right here. It's going to translate into the same thing. So what happens now is when I define this gain category like this, and I take this viewable category, I quotient it by the handle relation, which is genus 1 equals genus 0. Then when I take the additive completion and the Carubian envelope of this, I get exactly the category rep as t. So again, we start with cobordisms, and what we end up with is something that is algebraic. It's a representation category. So that's what happens when one takes a constant sequence. I just wanted to show here that, of course, you could take different sequences, right? So for example, if I were to take something like alpha 0 and then everything 0, so the generating function is constant, then I will get the representation category of that orthosymplectic Lie superalgebra, a different representation category, right? What happens if I take something that has like a linear generating function? Well, I can get something that's, this is like rep ST that we were just looking at, but it's rep OT, where O is the orthogonal group. So it's a similar construction that interpolates from rep ON to rep OT. And in fact, these are just two examples of, well, constant generating function, linear generating function, and in their paper, Kovanov, Ostrich either classify, depending on the generating function, what kind of category you're going to get, and or leave it as a conjecture. Sometimes it's hard to prove that these two categories are the same, but they conjecture what they could be. And how are all of these things done? Well, because what you're looking for is a Frobenius algebra. That's basically the thing that you need. If what you, the way that you define these things is you find a Frobenius algebra in the target category, in rep, in this case, rep OSP, that satisfies the same conditions as your linear recurrence alpha. So that's how the Frobenius algebra comes in. If you want to start with a functor to know that you have this functor, you need to find a Frobenius algebra. Okay. Any questions so far? So that is a story for the oriented case. So let me tell you a little bit about what is known in the unoriented setting. So I'm going to be talking just about two-dimensional things. Now, when we talk about the category of unoriented two-dimensional cobordisms, everything loses orientation, right? Before, when I defined cobordisms, everything had orientation. Now, everything is unoriented. And it's work by Turaev and Turner that this, again, has a nice description by generators and relations. So you can see now we have two extra generators. These are the ones that we had in the oriented case. Now we have two extra ones. One, which is the orientation reversing cylinder. This is what is tracking the orientation of any circle. And the other one, which is what we call the cross-cup generator. Basically, it has to do with a Möbius band. So here, I'm showing that we have now two different cylinders that we can compose. So if we do it the way that we always do, these two oriented cylinders, we get the torus. But what if we are composing one of these orientation reversing cylinders with a regular one? Then we get the Klein bottle, and the way that we would describe this with our generators is by this, by two Möbius caps, Möbius bands glued together. So you can see here, we're getting an orientable surface, but when we have something like this, we're getting an unorientable surface. And of course, if I'm giving generators, I should give the relations. So here are the relations. You can see all of this. So this is spelled out very well in on the original Turner paper, but also I even generalized a little bit by Tugendhauer in his thesis. So you can see all of this are the ones that we had for the oriented generators, right? But now we have two extra generators, which are the orientation reversing cylinder and the crosscut. So we get these new relations right here. So maybe let's look at these ones, which have the cross-cup cobordism. What this is saying is that in my category, trying to change the orientation of a circle when I have a Möbius band, that's the same as not doing anything. This is unorientable, so that doesn't change topologically my cobordism. And this having two Möbius bands is like, well, this is trying again to be the Klein bottle drawing, which is I am changing orientation somewhere inside of the torus. And of course, I have then also how the orientation reversing cylinder behaves with multiplication, multiplication, and all that. So the picture maybe to have in your heads right now is before we had just this one picture of what a connected oriented cobordism would look like. And now in the unoriented category, we have things that are orientable. So they look like the other ones, with the difference that in each circle, we can choose whether we have a regular cylinder or one of these that have the arrow inside, which is the other type of cylinder, the other generator, basically, which one of these we have in each circle. And then we also have things that are unorientable, right? Which are things that have, well, you can't, maybe you can see a little bit, but the difference for this one, it has no cylinders because it's kind of like we saw before in the relations part. Putting a cylinder when you have a cross cup is irrelevant. The cylinder goes away. And this is the thing that we have here that is making it unorientable. So what happens with unoriented TQFTs? The definition is the same. We want a symmetric monoidal functor, but now from the category of unoriented cobordisms. And so Turaev and Turner in their paper come up with this notion of an extended Frobenius algebra in the target category, which basically is to be able to say the data of an unoriented TQFT in the two-dimensional case is the same as finding now an extended Frobenius algebra in C. So what is an extended Frobenius algebra? Now we will need more maps. So this is the same as what we had before. The object with the multiplication unit, co-multiplication, and co-unit should be a Frobenius algebra, a commutative Frobenius algebra. And now I have two extra structure maps, right? Like they are relating to my two extra generators that I have. So one has to do with this orientation change in the circle. That's what we call phi here. And I want phi squared to be the identity. Maybe I should have shown that drawing here, but where do I have it? It might be that's missing here. But when you stack two circles that have this drawing, you should get just the regular one.
It's the middle on the first row of your phi.
Oh, thank you. Yes, okay, it's right here. So we want this when we do it twice to be the identity. So that is the first condition that we ask for all this structure map. And then these two diagrams right here is like the translation in an algebraic sense of the two topological equivalences that we have here. So one corresponds to this drawing and the other one corresponds to this other drawing. And that is what we call an extended Frobenius algebra. So we need to find a commutative Frobenius algebra, and now we need to find these two extra maps, one from the object to itself and one from the object to the field that's satisfied these commutative diagrams. So the thing with extended Frobenius algebras is that there's not as much work done, because work for commutative Frobenius algebras we know a lot, but extended Frobenius algebras are relatively new and not a lot of people have worked with them. I was going to take like a side, maybe one slide to say we did study extended Frobenius algebras with Kirsten, Quiñones, and Walton. And we were basically trying to come up with examples, right? Because like I said before, if you want to be able to build these functors, you need to find a commutative Frobenius algebra in the oriented case. Well, if you want to build these functors in the unoriented case, you need to find an extended Frobenius algebra, but we need to know examples then of these things. So let me show you this slide right here is this work with Kirsten, Quiñones, Walton. And so we were trying to say, what are some examples, what are some classifications of these extended structures? So let's look at, let's say we have a finite group G. And like I said in a previous slide, this is a Frobenius algebra and the co-multiplication looks like this. I think before I gave you the co-unit instead, which maps the unit to 0 and then G, sorry, the unit to 1 and then G to 0 for G and any other invertible. And in this case, I'm giving you the co-multiplication. You can give one or the other. You can always get one from the other. And so the question was, well, what are all the ways to have an extended structure? Because if you want something that is extended Frobenius, you need to start with something that is Frobenius. And now how can we extend it? Well, one easy way in which you can do it is just take phi to be the identity, and this theta element that you need to be a multiple of the unit. And that works. That satisfies all of the commutative diagrams, and it will give you an extended structure. So the question is that the only way in which you can extend Frobenius algebra like this? And we were able to, well, fully classify for some examples of groups, but the answer is no. For different types of groups, you can have different extensions, non-equivalent to each other. So for example, if I'm thinking of the cyclic group Cn, another way to extend is instead of taking phi to be the identity, I could send a generator G to a multiple of its inverse. Here, omega n is an earth root of unity. And then I could define this other object, the theta object like this, that would also give me an extended Frobenius structure on the Frobenius algebra. So you can see there are many different ways in which we can do this. And in fact, it's sometimes we are not even able to do it in any way. So that's the question right here. Are all Frobenius algebras extendable? The answer is no. Sometimes we have Frobenius algebra and we cannot find an extended Frobenius structure on it. So all this to say that, well, there's not that much that we know yet about extended Frobenius algebras, but why are they relevant, or where do they come up? They come up in unoriented two-dimensional TQFTs. That is the data that you need if you want to define a functor like that. Right, so here is just the drawing of why is it the same data. You can see here I have everything the same as before, except these two extra generators. You would map them to the respective structure maps that we just added to the Frobenius algebra. And then as long as you have an extended Frobenius algebra, which is to satisfy these two diagrams, that's going to be equivalent to these two equivalence classes that we have in the unoriented category. So everything works the same. We just have two extra generators. So now this is the work that I did. Now the thing is, before we were trying to linearize this oriented cobordism category, right? So I wanted to see how we could do a similar thing with unoriented cobordisms. And so one thing to note here is, because now we're working with things that are orientable and things that are unorientable, we have very different classes of cobordisms, if you want to think about it like that. And in fact, we can think of our drawings in three different categories. So one is the ones that are orientable. They have no Möbius spans. So these drawings are exactly the same as the drawings that we had in the oriented case, right? We are not using any of the two new generators, basically. But then we can have two other types of cobordisms, which are the ones that have one Möbius band or two Möbius bands, and these are both unorientable. And the reason we stop at two Möbius bands is because our generators say, whenever you have three Möbius bands, you can replace it by just one Möbius band as long as you go up in the genus. So these are the three types of surfaces that we have, and because we have three types of surfaces to use to define our linearization, we will use three sequences. Yes?
Sorry, maybe it's a silly question, but I thought topological surfaces were classified by just oriented or not and genus.
Yes.
So only two types. What are the three types?
Well, in the sense that you are saying it, the type 2 and type 3 would be in the same category, right? The thing is, when you're trying to use these when you're trying to see the relation between ones that have one cross-cup and the ones that have two cross-cups, there is no relation. So I could have just put them on the same category, but then when I want to use a sequence to define them, it's like I would need something that look like beta 0, gamma 0, beta 1, gamma 1, like they're independent of each other in a way. They are the same type of topological surface, yes, but algebraically it makes, you could do it not separating them, but separating them made more sense because there are no restrictions. One of them doesn't impose a restriction on the other. That's kind of the idea here. Does that make sense? Yes, they're both non-orientable. So they're in the same class topologically. Algebraically, because one of them having one cross-cup has no relation to having two cross-cups, I can just give them totally independent numbers. That's what I'm saying. And of course, you could track them in a different way, but you want to be saying what the number is for each surface, and this was the easiest way to do it in a way, because then you can just give 3 sequences and you're done. But that was actually one of the questions when we were thinking about this in the beginning. Should we just, because we have these 2 types of things, just put them all in the same bag and try to just use 2 sequences? But in the end, it always turned out that, well, these 2 things are very independent of each other, so we're having separate linear recurrences anyway, might as well just put them into 3 different sequences. Okay, so now we want to have finite dimensional Hom spaces again, and we want to, again, the only concern that we have is to restrict the genus, right? That is what makes these things infinite dimensional in the end. So here, once I have these 3 sequences, what I'm saying is I'm making it k-linear, same way that we did before. So I'm allowing for formal sums of cobordisms, and then I'm also replacing closed surfaces using these 3 sequences right here in the way that is written there. And now I want to control the number of the genus number of these surfaces, and then what I'm going to do is, same as before, I just quotient by the handle relation, and as long as alpha, beta, gamma satisfy the same linear recurrence, this will be the handle relation. Well, the technicality is this will be inside of the tensor ideal of negligible morphism, so I can consider the tensor ideal generated by this handle relation, and I can quotient this category, and everything works. And now I get something that is finite dimensional. And so after constructing this, of course, you have to be very careful to make sure, now that you're dealing with 3 different types of sequences, to make sure that what you're defining is okay. So that is one of the things. But after we are assured that we can define this, well, I was trying to see how I could come up with something that was, again, purely algebraic, so a representation category. And the first thing I looked at is what happens if I forget about unorientable things. So let's forget about unorientable things for a second, and let's think about the category of orientable but unoriented cobordisms. Technically, the thing I'm not saying is I'm quotienting the category by the ideal generated by the Möbius band, which makes it so that any unorientable thing is just erased from the category, let's say. And in that way, I can choose my alpha sequence to be constant and my beta and gamma sequences to be 0. So now that I lose orientation, that is the only difference between the other one that we were seeing before, right? When we were using a constant sequence and getting rep ST. Now what we're saying is, let's lose the orientation, what happens? And it turns out that what we get is this right here, which has a Ries product with C2. So there is an action of C2 there, which the way to think about it is at every circle, we have a choice of cylinder, a choice of orientation, because everything is unoriented here. And that's how it changes. Okay, let's now look at when we have orientable and unorientable things. So for example, I can take alpha, beta, and gamma to be constant sequences. Because all three of them are constant, they satisfy the same linear recurrence. That doesn't mean that alpha 0, beta 0, gamma 0 have to be the same number. They can be different numbers, but they satisfy the same linear recurrence, which is genus 1 is genus 0, basically. Then what happens when I do this construction is I get a product of first, the one that has the Reith product, which you can think of it as corresponding to this type of cobordisms, the one that are unoriented but orientable, and we can choose a cylinder at each end. And then we have these two other types, which correspond to whether we have one Möbius band or two Möbius bands. And so I do the Deligne product of these two categories, and I get back the construction that I came up with topologically. And so how does something like this work? Well, you have to find extended Frobenius algebras. So that's a main component of this. You have to be able to find the respective extended Frobenius algebras, and that's your starting point. And then, well, there's a lot more work involved with proving the equivalence. Yes, that is your starting point. And of course, you can say exactly what all of these parameters are. And that's it for my talk. Thank you.
Are there any questions? No.
In the oriented case, if I take my Frobenius algebra to be separable, I can construct my TFT as a state sum TFT with defects. Can sort of an interesting statement be made for the unoriented case if I take the extended Frobenius algebra to be separable?
Yes, actually, if the Frobenius algebra is separable, then you can always extend it. So that is a good first start, because we have this condition where, sorry, we have this result where not every Frobenius algebra is extendable, right? If your Frobenius algebra is separable, there's always one way in which you can extend it. So from there, you should be able to get an extended Frobenius algebra, which is the first step for the unoriented construction.
Do you have a sense of like a classification of the type of representation categories you should be able to construct in this way?
In the unoriented case?
Yeah.
No, because we don't have that many examples of extended Frobenius algebras, right? When you want to do it for the oriented case, then you just go and you find a Frobenius, which is also complicated, right? To find a Frobenius algebra that is not in vector spaces. So for example, to find an extended Frobenius algebra that it's useful for something like this, I have to go to this diagrammatics right here. So let's go to RepST here. And you have to think of, well, the algebra should be just one dot. And then how do I define the product and the coproduct and the unit and the co-unit using partitions? And then how do I make it so that the dimensions, because there's you have to make the dimensions of the home spaces match, which has to do with the evaluation, right? And so you can kind of do it. And for my construction, I had to do, it's not the same diagrammatics because we have this Reith product, but there's this very nice paper by Masaki Mori where he does, so for a symmetric category C, or for a monoidal category, tensor category C, you can define this functor ST of C, which gives you a new tensor category, and there are diagrammatics for this. When you choose C to be Beck, you get RepST. When you choose C to be the representation of a group, you get the Reith product. So you can use his diagrammatics instead of these ones. And then you have to be able to define an extended Frobenius algebra there. But in general, you would need, again, to define Frobenius algebra somewhere else. And we don't understand the sorry, and that was a problem, yes. But I think it's an interesting question, changing the sequence alpha and trying to find what you get, like they did in the oriented case, but in the unoriented case, yeah.
there are no further questions, then let's thank Agustina again. I believe there's a coffee break until 10:30, right? No, 11:30, sorry.
Don't we do, maybe we anticipate because maybe half an hour is a little bit too much, I don't know. If you promise me, but you remember to come back.
No, it's okay, it's okay.
It's okay. So let's take it.